So in tonight's lesson, we're going to talk about the definite integral. So the first thing that we need to know that we're going to be able to do at the end of this lesson is we want to be able to write the definite integral as the limit of Riemann sums. Then we need to be able to use the limit of Riemann sums to evaluate a definite integral over a closed interval starting from 0, and then over an arbitrary interval from a to b. Then we're going to be able to use formulas from geometry to determine definite integrals, and then use definite integrals to determine the total area and net area. So the Riemann sum we actually covered in the last section, and we saw that the sum in terms of n subintervals was the sum of all of the widths multiplied by our heights. Then we saw to get the exact area, we took the limit of that sum as we went to infinity. So before now, we were calculating the Riemann sum, then taking the limit and getting the exact area. However, this operation, when we do it, is equivalent to setting up the integral from a to b of our original function in terms of our variable x. So we're going to actually use antiderivatives to see how to evaluate these integrals. A couple of facts we need to make sure we have down before we start tonight's problems are, the first is you will get the same answer for the integral as you do from doing the Riemann method, but if the integral exists, then we say f is integrable on a to b. So that means this statement works in reverse. If we tell you a function is integrable, then that means you can evaluate the integral itself. A and b are the upper and lower limits, and just like always, we read it from left to right on the number line. So a is the first value, and b is the second value, or the right side of our interval. Area is always going to be a non-negative quantity, but so if we want the definite integral, it's the areas above the x-axis minus the areas below the x-axis. When we talk about area, it's implied that we mean total area. So the integral, if you don't separate your two regions, gives you what's called the net area. So the net area takes the positive values and the negative values, adds them together, and then just gives you what's left over. So total area is here, and that will end up being a non-negative quantity, because if these regions are negative, when you subtract, it turns into a positive number and we get the total area of the region. However, the net area could be a negative number because it's telling you, well, if it's negative, there's more area below the x-axis than above the x-axis. There's some properties of the integral that we need to make sure we understand. If you reverse the order of these limits, well, then you get the same value in the integral, but it's now the sign is changed by -1. If you are going from the same value to the same value, so from a to a, that area is 0 because you basically have no width. Just like with sums and derivatives, you can distribute the integral if you're adding up a bunch of terms. So if we have the sum of two terms, it's the same thing as evaluating the integral for each piece. And constants will factor out of the integral. So if you have c times a function, you can pull the c out front, evaluate the integral, and then multiply by c. We can also split an integral into two pieces. So if I'm thinking about this interval on a number line, there's a, there's b. For any value c, the integral from a to b is the same as if I just take the area from a to c and then add it to the area from c to b. So if you notice here, when we split, the value you end has to be the value you begin with on the next integral. Then we have the dominance principle, which says if f of x is always greater than g of x, then the area under the curve for f of x will give you a larger area than the area for g of x. The last thing we're going to talk about is the max-min inequality. So if little m and capital M are the minimum and maximum values of f, meaning the smallest y and the largest y value, then we can use this formula to approximate the area of the integral. So we can say, well, the minimum value, which is the height, times the width of the interval we're looking at, will be less than or equal to the true area which will be less than or equal to the maximum height of the function times the width of the interval. So this is still length times height, and this is length times height. So the true area lives in between these two values. The average y value of f says, well, if I compute the area, which is going to be in some quantity squared, and then I divide by the width of the interval, it's going to give me the average of all the y values for the function over that interval.